Hello, it's an honor to give a presentation today. My name is Ho Sang-moon. I'm a student from the Department of IT Semiconductor Convergence Engineering at Korea Polytechnic University. The objective of my presentation is to propose a method for establishing environments of driving simulation and scenarios that can evaluate the visual behavior of elderly drivers quantitatively according to static and dynamic visual stimuli using analysis of text network. Let me explain it in detail on the next page. Aging has been considered a global problem for a long time as a result of demographic change occurring in many countries without exception, developed and developing both. In particular, the aging in Korea is progressing faster than in other countries. The graph on the left side of the screen shows the increasing trend of the elderly population aged 65 and over in Korea predicted by the Statistics Korea. Korea has already entered a society at 15.7% of the proportion of elderly people in 2020, and it is expected to reach 20.3% in 2025, which means entering into a super-aged society in the next 5 years. In addition, it is expected that at least 43.9% in 2060, and about half of the domestic population will be composed of the elderly. Accordingly, the proportion of elderly drivers is also increasing naturally. As seen on the right side of the screen, you can see that the number of fatal accidents has been decreasing over the past 6 years, while the proportion of elderly drivers and the number of traffic accidents caused by them is increasing every year. The Korean government has announced policy for the elderly to voluntarily return driver's license as a social effort to reduce the incidence of traffic accidents caused by elderly drivers. This policy encourages elderly drivers to have a transportation card worth 100,000 won as a benefit. Due to the policy, the ratio is increasing, but it is still low. Furthermore, it is required to institutionalize the factors that can objectively evaluate the driving ability of elderly drivers, because it is conducted based on subjective judgment. In this slide, I focus on the driver's information processing and visual behavior. In general, the information processing for various traffic environments required of drivers is largely classified into 4 steps in the order of sensory detection, perception, decision-making, and control response. In particular, elderly drivers have a relatively high probability of accidents because their cognition and decision time increase due to physical aging. Most of the information necessary for driving consists of visual information, and the deterioration of the visual behavior ability to quickly identify and react to objects and vehicles in driving situation is one of the biggest cause of accident. Visual behavior, which refers to the process of recognizing and responding to information received by visual stimuli, can be divided into visual detection, visual perception, and visual motor function. First, visual detection belongs to a stage for cognition as a process in which the driver visually searches for various information collected from the surrounding environment while driving. It is known that elderly drivers have a relatively narrower area of vision than ordinary drivers, so the area of interest is narrow while driving, and the frequency of scanning the same area of interest tends to be higher. Visual perception is a step for the drivers to recognize, analyze, judge, and respond to external stimuli. In the case of the elderly driver, the information processing for external stimuli is slower and the response time is relatively longer than that of the general driver, because the function of visual perception decreased due to the deterioration of the cognitive function. Visual motor function is a step in which drivers properly control and react to the vehicle after the cognition stage and can be confirmed by drivers operating the steering wheel and pedals according to external stimuli. When the control of the vehicle is finished, the environment around the vehicle and the visual information are switched, and this procedure is repeatedly performed while driving. It is necessary to construct appropriate driving environment and scenarios to check the driving characteristics of elderly drivers in order to evaluate the driver's visual behavior quantitatively using a driving simulator. In this research, we tried to utilize the driving environments and scenarios of existing literature as a method to implement a driving simulator to evaluate the visual behavior of elderly drivers. As a result of searching the literature published up to June 2020 by selecting 5 academic databases that used frequently, total of 1,453 documents are correct. 243 cases from EMBase, 281 cases from SciInfo, 206 cases from PubMed, 487 cases from Science.Direct, and 236 cases from Web of Science. The literature search strategies divides keywords into 4 types, consists of participants, disease, intervention, and outcomes. Among the total documents correct, 263 documents with titles and others found as duplicates in one or more academic databases are removed, and leaving 1,190 cases. And researchers reviewed the title and abstracts. It was removed 993 documents that are not suitable for inclusion criteria, resulting in 197 select documents related to traffic accidents involving elderly drivers and using driving simulators. In the remaining literatures, 68 documents of inconsistency in research goals, 2 documents not written in English, 4 documents for which the full text could not available, 63 documents with an average age of less than 60 years in the elderly drivers group, 23 documents comparative studies on the driver group disease, 5 documents comparing vehicles and driving simulator, and 3 documents in which crashes and driving conditions are not specifically described. We exclude all of them, and finally 29 literature are select. A centrality analysis of keywords was performed to identify major driving environments and scenarios by external types of 29 documents finally selected in the previous slide. Density, average distance, centrality analysis, and component analysis are widely used to examine the characteristics of connected keywords. The most used index is centrality, which has the advantage of quantifying the frequency and connection strength according to various types of centrality by analyzing keywords that play an important role in the network connection. Centrality is an index that expresses the degree to which keywords play an important role in the overall network, and its types include degree centrality and between centrality. The degree centrality refers to the number of keywords linked with keyword. A higher centrality indicates that the keyword is linked with the many other keywords. The calculation for the degree centrality can be shown in the upper left corner of the screen. The between centrality represents the extent to which a keyword lies in the shortest path between 2 other keywords and indicates the number of keywords located in the path in the network. In other words, It implies that the keyword in the middle position plays the role of a broker and connects other keywords. Between centrality can be calculated using equation at the bottom left of the screen. In this research, we visualize the degree centrality via size of the node and the between centrality index between the keywords via thickness of the links that connect two keywords. The higher degree centrality, the larger the circle, and the higher between centrality, the thicker the line. For example, in the accident type classified as single car, car to pedestrian, and car to animal, degree centrality and between centrality are the highest in the type of car to car, because it can be seen that the size of circle is large and the line is thick. This slide shows scenarios in intersection based on the result of text network analysis. The types of intersections are divided into controlled and uncontrolled, and the scenarios at the controlled intersections are more diverse. However, since the driving simulation content to be implemented in this research is evaluation of the driving ability for static and dynamic visual stimuli in urban driving environment. Scenarios that evaluate the driver's specific cognitive domain or the ability to control vehicle functions are excluded from the list. Excluded items are the 5 scenarios at the intersection marked in red font. This slide shows scenarios for a 2-lane highway, and they are found to have the most types of our driving environments, and scenarios that inconsistent with the research goals are excluded as described in the previous slide and displayed in red font. You can see that the scenario in which animals appear is excluded additionally. This slide shows scenarios in 3-lane and 4-lane highway. Here too, scenarios that inconsistent with the research goals are excluded. In particular, in the case of 3-lane highway, it can be seen that all scenarios are excluded because it is a driving situation on an expressway. The visualized results of reclassified driving environment and driving scenarios by analyzing the text network for static and dynamic visual stimuli in visual detection, visual perception, and visual motor function using the remaining scenarios are shown in the picture on the screen. As a result of text network analysis, it was found that stalled car, traffic lights, and signs are used as static visual stimuli, and moving vehicle and jaywalking pedestrian are used as dynamic visual stimuli. In this research, the contents of evaluating visual behavior and appropriate scenarios are selectively applied. It can be seen that stop or go, which requires searching for change in traffic lights that appear around driving drivers, is applied to the scenarios related to static visual stimulation, and cutting line, turning left, and turning right, which need to explore change in the surrounding environment, are applied to the scenarios related to dynamic visual stimulation. Visual perception is to check the time from when driver recognizes external stimuli to before finally react by analyzing and judging the surrounding information. And speed limit connect to traffic sign, and avoiding stalled car connect to a stalled car are applied in scenarios related to static visual stimulation. Traffic sign is a stimulus that does not change, unlike traffic lights or tail lights of vehicle, and it applies a scenario for confirming the driver's perception, analysis, and judgment rather than visual detection. Contents for visual motor function that recognize and respond to external stimuli are applied reversing vehicle collision, sudden brake, and jaywalk that can confirm behavioral response to dynamic visual stimuli in unexpected situations. The road that the driver drives in the impermanent content proceeds in the other. Based on these results, the scenario design for the evaluation of drivers' visual behavior according to static and dynamic visual stimuli are merged the similar types into the driving environment with a higher frequency of occurrence and many visual stimuli factors. For example, reversing vehicle collision occurred more frequently in two-lane highway than intersection, so the scenario was applied in two-lane highway. In the case of turning left and turning right scenarios, it was applied to the uncontrolled intersection rather than four-lane highway. Because visual detection of drivers during just driving is evaluated without certain factors in four-lane highway, but visual behavior according to dynamic visual stimuli such as moving vehicles and pedestrians crossing the street at a crosswalk can be evaluated in uncontrolled intersection. Furthermore, scenarios such as sudden brake, jaywalk, and stop or go are implemented in both driving environments because the factors for evaluating the driving environment and visual behavior are different. The driving environment and 12 scenarios finally select route through this process shows in this table. The route that the driver drives in the impermanent content proceeds in the other of uncontrolled, controlled, uncontrolled, controlled, 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 based on the driving environment at the intersection, and the order in which scenarios are set up randomly. For example, when the vehicle at the start point arrives at the controlled intersection of section A, it is driven by selecting turning left or turning right. Turning right is selected here. Next, in controlled intersection of section B, any scenario among sudden brake, jaywalk, and stop or go is set. In the uncontrolled intersection of section C, the scenario except for the scenario performed in the uncontrolled intersection of section A is set. Turning left is selected here. In the controlled intersection of section D, any scenario among the remaining two scenarios is set except for the scenario performed in the controlled intersection of section B. In the controlled intersection of section E, a scenario is set except for the two scenarios performed in the controlled intersection of section B and section D. And all scenarios in the round-trip lanes placed between intersections are also randomly set. The driving simulation contents implemented in this research aim to evaluate driving ability based on the visual behavior of elderly drivers according to static and dynamic visual stimuli in VR environment. Therefore, gauge information of drivers responding to various stimuli presented to them is obtained by acquiring information on gauge fixation and saccade using eye tracker mounted on the HMD. And the behavioral reaction to control the vehicle is obtained through the steering wheel and pedals of simulator. The current slide shows the proposed indicator for evaluating the driver's driving information. Gauge fixation means that the gauge of drivers temporarily stays at one point for more than 200 milliseconds in the process of scanning the surroundings, and saccade means that interval of the distance or time from gauge fixation to the next gauge fixation. Visual detection used as an evaluation index is evaluated by the ratio of stimuli actually searched for by the drivers with respect to all given stimuli, and visual perception can be evaluated by measuring the reaction time from when the target stimuli occurred to when the gauge is fixed to the target. In addition, The evaluation of visual motor function is performed by measuring reaction times such as the steering wheel or brake pedal in response to a target stimulus. From the current slide, I'd like to explain the result of improvement content. First, the uncontrolled intersection content with no signal from the traffic system, which depend on the driver's visual detection, consists of turning left and turning right scenarios. In turning right, the driver's vehicles aim to explore the driving route and speed of the oncoming vehicle and have to turn right with a collision. The oncoming vehicles in the first to cross, and after the next left vehicle has passed, the driver must turn right. Similarly, in turning left, the oncoming vehicle crosses first and the driver must turn left after the left and right vehicle have passed. The driver's visual detection ability is evaluated by the number of times the driver gaze is fixed on the nearby vehicle presented by a visual stimulus. At this time, the number of fixation means that the driver's gaze is fixed to the present target for 100 to 200 milliseconds or more. That is the ratio between the number of target stimuli present here and the number of target stimuli in which gaze fixation has occurred in an index of visual detection ability. The content of the controlled intersection consists of sudden brake, jaywalk, and stop-or-go scenarios. In sudden brake and jaywalk, visual motor function is evaluated when visual stimuli such as leading vehicle or pedestrian is presented to the driver. And in stop-or-go, visual detection is evaluated in response to target stimuli such as a traffic light. In the sudden brake scenario, the driver aims to make a left turn without collision while searching for the leading vehicle, and the main target stimulus is the tail light of the leading vehicle. Here, the visual motor function is evaluated by measuring the reaction time of steering wheel and brake pedal operation after the saccade, which means the difference between when the tail light is turned on and when driver recognized. Jaywalk is a scenario in which the driver recognizes pedestrians crossing the road and turns right without collision to pass the intersection. Pedestrians who suddenly appears from the sidewalk blocks on the right side of the driver's vehicle is presented as the main target stimulus, and the time it takes for the brake pedal or steering wheel to be operated after the saccade is evaluated. In the stop-or-go scenario, when the red light of traffic light is on, the driver recognizes through visual detection and aims to stop before reaching the stop line. By measuring the number of gaze fixation on the traffic light, the degree of driver's visual detection toward the traffic light is evaluated. Next is the content for the two-lane highway scenario. First, in the reversing vehicle collision scenario, the driver's perception time and the reaction time of pressing the brake pedal are evaluated for a reverse traveling vehicle driving over the center line from behind the bus. The moment when the reverse traveling vehicle crosses the center line is regarded as the time when the target stimulus is present, and the time from when the driver's gaze is fixed to the time when the brake is operated is measured. This is to evaluate the visual motor function, and it evaluates the difference between the time the driver perceives and the corresponding behavioral reaction time for the target stimulus. Speed limit scenario evaluates the visual perception that measures the time it takes the driver to recognize a speed limit traffic sign in a children protection zone and operate the brake pedal. Here, the time it takes for the driver to recognize the traffic sign is measured by the time difference between when the drivers enter the marked lane and when the driver's gaze is fixed on the sign. It is possible to evaluate whether the perception is correct by ensuring that the driver stays below the speed limit of 30 km per hour on the road covered with red asphalt. Stop or go in the two-lane highway is a content to find out whether a signal change can be quickly recognized by sufficiently detecting the traffic light set as the main target stimulus. In the same way as stop or go scenario at the control intersection, the number of gauge fixation on the traffic lights and detecting the main target stimulus after the signal change are evaluated. Finally, the contents of foreign highway scenario are improvement. The sudden brake scenario evaluates that the driver searches for the tail lights of the leading vehicle and drives while assuring a safe distance. This is the same as the evaluation criteria and the main target stimulus when sudden brake at control intersection. Similarly, the jaywalk scenario is a pedestrian crossing on the road, which is evaluated in the same way as jaywalk at control intersection. Avoiding stalled car and cutting line are scenarios in which the driver recognizes and avoids a vehicle that is stalled in the same lane when turning right. Then driver have to search for left lane sufficiently and cut into the left lane without a collision. In avoiding stalled car, the visual perception ability for static target is evaluated by measuring the time taken from driver turn right and enter the same lane as the stalled vehicle to recognize the emergence light of the stalled car. On the other hand, in current line scenario, the number of times the driver's gaze is fixed on the main target stimulus consisting of one vehicle stalled in front of the driver, one vehicle driving behind the left lane, and the left side mirror of the driver's vehicle is used to evaluate whether the driver is sufficiently detecting to cut into another lane. When you come down to it, this research aims to implement a driving environment and scenarios of driving simulation that can evaluate the driver's visual behavior with respect to static and dynamic visual stimuli that occurs in various driving situations. As a method for this, 1,453 related literature are correct. 29 literature are selected through review of inclusion and exclusion criteria, and driving environments and scenarios are extracted through text network analysis of the driving simulation used 29 literature. In addition, the driver's visual behavior was divided into visual detection, visual perception, and visual motor function, and the driving environment and scenarios are reclassified and merged through text network analysis of static and dynamic visual stimuli. As a result, static visual stimuli composed of stalled car, traffic lights and signs, and dynamic visual stimuli such as moving cars and jaywalking pedestrians are included. And the driving simulation contains consisting of a total of 12 scenarios in controlled intersection, uncontrolled intersection, two-lane highway, and four-lane highway arrangement. Each scenario has different primary evaluation factors for visual behavior, which is measured through the number of gauge fixation, circuit time, and behavioral reaction time. The degree and distribution of the driver visual detection can be confirmed through the number of gauge fixation for all the present target stimuli. And quantitative evaluation of the driver's cognition and response is possible through the reaction time when the gauge is fixed to the target stimulus and the reaction time to operate the steering wheel or pedal afterwards. In this research, no comparative experiments are conducted according to the actual driving experience and age of the driver, but an additional test process that can set criteria and ways to be applied to visual behavior evaluation in the future is required. In particular, in order to prepare a guideline for quantitatively evaluating the driver license, return criteria for elderly drivers, it is first necessary to analyze the driving characteristic of the elderly driver's visual stimuli. By the end of this presentation, I hope that if the results analyzed in this research are used as basic data to create evaluation contents to induce elderly drivers to voluntarily return their driver's license, it will be possible to make them feel the need to return their driver's license by providing more objective evaluation criteria and quantitative results. That concludes my presentation. Thank you very much for your listening.